Everyone, welcome to Clean Coder YouTube channel. So in today's tutorial we are going to discuss problem number 230, Kth smallest element in BST. So again, this is a commonly asked interview question, so we are going to discuss some of the approaches which you can give to the interviewer in the interview. So this is a medium level problem, so it's good if you will solve this on your own. So let's go through the problem statement first. So given the root of a binary search tree and an integer k, return the kth one index smallest element in a tree. Okay, we'll go through the example, but let's move below to read the constraints. So the number of nodes in the tree is n, and they have given a range between k and n is in 1 to 10 raised to power 4, and the value of the nodes won't exceed 10 raised to power 4. Okay, so this follow-up question will take at the end. So let's move to the whiteboard and let's try to discuss this problem there. Okay, so this is a test case which they have given to us, right? So there's a binary search tree, right? So what they want is they'll give a k. Okay, this along with this binary search tree they'll give a k. So k could have any values, like k could be 1, k could be 2, k could be 3, k could be 4. So if we write the in order traversal of this binary search tree, right, so it would be something like this. Okay, in order traversal would be 1 2 3 4. So if they give k equal to 1 as input, so we are supposed to return the smallest element. Okay, so the smallest element is 1. So if they return, if they give us k2, then we are supposed to return second smallest, right? And if k is 3, then we are supposed to return third smallest, and so on and so forth. So I hope the input and output are clear to you. Let's move to the different approaches which we can use to solve this problem. So I mainly written two approaches which you can follow. The first approach is a kind of brute force solution, but in this question you can see that even brute force solution is not that bad, and if you are able to explain it well in the interview, then even interviewer could agree on this approach also. So what this approach one is, store the in order traversal in an auxiliary array, right, as we have done in the for the previous test case. So for this binary search tree, we'll store the in order traversal in an array, right? Now once we have this auxiliary array, we can directly return the element they are asking. Like if they are asking smallest element, or they are asking second smallest element, so the result of that query could be returned in of 1. So this is also a good solution, but there are pros and cons which we'll discuss. But first let's see the time and space complexity trade-off for this approach. So for this approach we are populating the auxiliary array by doing a in order traversal of the binary search tree. So time complexity is O of n, and space complexity would also be O of n, because we are using an auxiliary array to store all the binary search tree elements. So now let's also discuss the pros and cons associated with this approach. So as I have told, subsequent request will be O of 1. So assuming your binary search tree is not getting modified a lot, and interviewer specifically states that there are a lot of retrieve operations, and comparatively there are not insertions or deletions much, so this is a really good solution for those types of constraints. The con, on the other hand, is if there are sufficient insertions and deletions and binary search tree is getting modified, then we are required to generate this auxiliary array repeatedly many times. So this solution is not a really optimized solution in that case. So let's move to the second approach, which you can talk about in interview. So the second approach is do a in-order traversal each time and find the kth element in it, right? So in that case, what we would be doing is that, assuming like I have a binary search tree like this, 1 2 3 4. Okay, this is my binary tree which they have given to me. Okay, so what we'll do is we'll do in order traversal. So this would be my minimum node, this would be my second minimum node, assuming they are asking me second minimum node. So when my in order traversal would reach here, I'll start returning from the recursive calls. Okay, so in the worst case, k could be equal to n, right? They could be asking the last node of this binary tree. So in worst case, I may need to do in order traversal of the complete tree, right? So the time complexity of this approach is again O of n, but the space complexity this time is only log of n, because at any point I won't be storing more than the height of the binary tree number of nodes in my stack. So let's discuss the pros and cons associated with this approach. So pro, I have already talked about. This is good when BST is getting modified frequently and there are a lot of inserts and deletes happening. So this is a good approach in that case. Con is we are supposed to do a complete in-order traversal, and which itself is O of n operation. So each time we are doing that, that is not a great approach, but like it's fine. Like if the given constraints are like inserts and deletes happen a lot. So let's discuss this approach code also in detail. Okay, so this is the code I have submitted. I'll explain this code line by line, and hopefully you'll be able to understand how to solve this problem recursively. So this is the function they have given to us. They have given us a root of the binary tree and a k parameter, and they are expecting a element at like kth position in sorted order, right? So that they are expecting. So what I am doing is that I am taking a index which would persist in the recursive calls, like something similar to pass by reference. So pass by reference I am accumulating with the pass by reference I am accomplishing with the help of array of size 1. You can make your own separate class also, but like this is a good hack if you want pass by reference in a recursion in Java. So this parameter I am passing here, and k they are passing, and binary search tree root they are giving. So now we'll move to this recursive function aux. So let's check the recursive calls first. So this is a simple recursive call, root.left k array and root.right k array. So whatever I am doing here is this will count as manipulations in order traversal, right? Because I am doing my manipulation inside the two calls. So what I am doing is this is incrementing the index in order traversal by 1. So array of 0 is acting like my index. So index plus equals to 1. This is similar to this. Okay, this operation. And if array 0 is k, if index is k, like this is the element which they are requesting, I am directly returning root dot value. Now I have written some if conditions here, right? So if left is not equal to integer dot max value, like when we reach the null value, I'm returning a really large number from those recursive calls. So when the left or right is not returning really large number, this means that they have got the kth element. So in order to terminate this recursion early, basically I am using this sort of an optimization. If you don't want to use these types of optimization, then it is also fine, just that it will optimize in case k is less than n. If k is comparable to the size of the like k is at the end of the in-order traversal, then this optimization doesn't help a lot. So yeah, this is the main crux of this algorithm. So if you want to dry run this code on a sample input, you can do this. Like let's take this example, 5 2 okay 3 and 6. So this is the binary search tree which they have given to me. Okay, so assuming k which they have given to me is 1. Okay, so what would be the element in that case returned? So element in that case should be smallest element, which is 2. So 2 is my answer in that case. So what would happen? I'll start my recursion from here and I'll reach this function. My index would be 0. So I'll execute this line and I'll do a recursive call to the left side. So now I'll move to the left side. Okay, so now I'm here, right? Again I'll move to the left side, but now what happens is there is no left child, like this is null, right? So this base condition would execute and it will return a really large number, infinity. So I'll reach here at 2 and I'll increment my index, which was earlier 0 to 1, right? So at this moment you can see that my requested element k is also 1 and index is also 1. So this means that this is the answer which was asked in the problem. So I'm directly returning this value, okay, root dot value. So this will return 2, right? So now what would happen is, like, this recursive tree I didn't execute. This is the optimization. Like, I already know that answer is not here because answer is already returned here. So this is a good optimization. Now for 5, I've already received left value as 2. Now for right one, I'll increment my array and it would be 2 now. So this won't execute because array of 0 is not equal to k anymore now. So right, it will go to here again, like it will do here, and this will return infinity, this will return infinity again, this would return infinity, and non-infinity value it will get returned. So I'll get my answer as 2. So this is the recursive solution which you can write in interview setting. So this was all I wanted to talk about. Now let's take that follow-up question which they have mentioned. So they are telling that if the BST is modified often, that is, we are doing a lot of inserts and deletes, and you need to find the kth smallest frequently, how would you optimize? Okay, so in that case, what we can do is we can modify the tree data structure itself, right? How we are going to modify the tree data structure? Like, we'll have an additional node here, like number of nodes in the left subtree. Like this is my binary tree, assuming. Okay. Okay, so there would be an additional parameter here which would tell number of nodes on the left side of the binary tree. So this would be 3, this would be 1, this would be 0, this would be 0, this would be 0. So when like for example they are asking me the 4th smallest element, right? So from here itself I can directly say that the answer doesn't lies here, right? Answer could be this or lie on the right subtree. So this is a kind of optimization we could have in that case. For this we are supposed to modify the tree structure itself, which interviewer might not allow, but this is a good optimization you can talk about in interview setting. So if you liked my explanation and my tutorial, please like this video, please subscribe to my channel Clean Coder, and thanks a lot for watching this tutorial, and have a great day.